Hello everyone. Welcome to our fourth and final installment for the 4.5 notes. Here we're going to solve some logarithmic equations where we are not able to use the equivalence property of logs in order to solve it. We'll have to be a little bit more creative. What we're going to do here is we are going to use basically what we've done before with the logs, how we've simplified logarithmic expressions using an exponential form. And what we're going to do is this thing that's called exponentiating. If I can spell it, exponentiate an equation. So something that we can do for exponentiating, of course, this is kind of what we've seen before, but it's a little bit of a backwards application of the equivalence property of exponents. Because what we had before was if you have the same base and you raise it to different exponents, then that means that those exponents actually are the same. Now imagine we start out with things that are equal. We know that something is equal to something else. Oops. Then what we can do is we can put these as the exponents on the same base, and we will know that this is also true. And so this is the equivalence property of exponential expressions, but here we're calling it exponentiating an equation. So we're going to take this equation and turn it into some exponents over here. That's why it's called exponentiating. And what we will do is we will choose the base creatively to match the base that goes onto the log. And what we will have, let's see how it will work. Since we have log base 5 on the left side over here, we should use 5 as our exponent. So I'm going to write it this way. We're just raising 5, the base of 5, we're raising it to the exponent of each side. Now we have this nice property for logs. Since the function that goes 5 to the x power and the other function that goes log base 5 of x, since these are inverse functions for each other, if we do this kind of a structure, what we have on the left side, where we are composing those two things, we have 5 and then raised to the power log base 5 of something, the answer will just be whatever is the argument inside of here. And so this left side simplifies, just becomes 3x plus 1 equals, on the right side it goes 5 squared. Now there's another way of thinking about this one, because we used before, when we were simplifying logarithmic expressions, we used this thing of converting a logarithmic expression into an exponential one using, I called it the loop-de-loop method, which of course you see in this example right here, we could go like b to the k power is equal to x. We end up achieving the exact same thing here as if we do the exponentiation, because you could imagine as well, if you raise both of these things, the log base b of x, and then we have that's equal to k, if we put these as the exponents for the number b, then here b to the log base b, it kind of cancels as it were, it just becomes x equals b to the k. And so here if we did b to the k power equals x, by doing the loop-de-loop method, we actually end up with the identical expression. For me personally, I think of it in terms of the exponentiation, where we use these as the exponents on both sides. It allows us to use it, I feel, in more contexts, but either way it works. And so here, 5 squared of course is 25. That's equal to 3x plus 1. We can subtract the 1, of course. 3x is equal to 24. And then when we divide by 3 on both sides, we will get that x is equal to 8. So that's how this problem will go. What about though for a problem like number 15? We can, at the beginning, we can just exponentiate both sides right away. Or we would have an option that if we move all the logs to the same side, since these logs have the same base, they're both base 10, when we move them onto the same side, we'll be able to use one of the properties of logs to write it as one log. And so we can do it that way first. Why don't we give it a shot? We can add log of x onto both sides. And then on this side it will go log of x plus 15, and then it goes plus log of x is equal to, here log of x cancels on the right side, is just equal to 2. And then we're able to use the product property over here to say that this sum of the logs is actually log of x plus 15 times the other argument times x, and this is equal to 2. Now we can, at this point, we can do the exponentiation, or else you can think of it as rewriting this into an exponential form. But I will put this, since it's log base 10, I will raise it to the power of, where it's on each side with a base of 10. And 10 to the log of this thing, it would just become this thing. So it would go times x. And then here, 10 squared, of course, is 100. So I'm going to continue it up here. We actually have a quadratic expression now, so we're going to get a couple of solutions for x. We can talk about what those solutions are, what it means to have multiple solutions. But here, what do we have? X times x, I'm just distributing this one. It goes x squared, and then it will go plus 15x. And then I'm going to say it's equal to 100, but I would like to subtract 100 on both sides. Because naturally, whenever we're trying to solve a quadratic equation, we need to have everything on one side and say it equals 0. And now this problem, is it possible to factor this left side? Do you see these factors here? It will go x with something times x with something. Things that will multiply to give 100, they add up to 15. So what about 20 and the minus 5? This will work. And so here, this is equal to 0, so we actually end up with two solutions. X is equal to negative 20, or x is equal to positive 5. Now we have to check these solutions to see if they work in the original equation. Because always when we're doing some of these kinds of things like rewriting into exponential form, or what we've seen before solving radical equations when you square both sides, some of these kinds of operations that we do, they can end up producing some extraneous solutions. So we want to always check our solution in the original, especially with log, because you know log has a restricted domain. When you just have log of x, f of x is equal to log of x, the domain for this one, it has to be only positive numbers inside of there. So if we try to take log of 0 or of a negative number, it is going to be undefined. We cannot have that. And so here, you notice in the original we have this kind of thing like log of x. If you try to plug in negative 20 into there, or indeed if you try to plug in negative 20 into log of x plus 15, it will go x is equal to negative 20. It would be log of negative 5. And we cannot take a log of negative numbers. So this one is extraneous solution. But we could verify that 5 actually works in the original. And so we have here only the one solution that x is equal to 5. And so this will be our general tactic for solving logarithmic equations. We've seen now logarithmic equations, exponential equations, all of the ways of solving them. All that's left now would be to practice some more, because you can see so many kinds of examples and ways that you can apply the different properties of logarithm, and in order to simplify equations, simplify answers, in order to obtain these kinds of structures that we want to apply these properties. And we will see moving forward some applications for the exponential and logarithmic functions, which basically applications, it means we're going to be using them in a context of word problems. And so that will be the subject for 4.6. This does it now for 4.5, and I will see you guys in the 4.6 videos. So thank you for watching.